All right, guys. I thought I would post a video to go over the answers to the questions that I gave you based on the note and video that you looked at today on the introduction to light and optics. So I will give the answers and kind of give an explanation. Sometimes it's easier to understand things when they're explained as opposed to you guys just reading it. So here we go. All right. First question asks, which has a shorter wavelength, microwaves or ultraviolet waves? And before I answer that, let me just reiterate a point that hopefully you got when you looked at that video and read through that note. And that's that all of these types of waves from, radio waves to microwaves, ultraviolet waves, all the way to gamma waves, they are all different types of light. So all of those things are light. They travel at the speed of light, which is about 300,000 kilometers per second. And we're used to thinking of light as that very narrow range in the electromagnetic spectrum that your eyes are able to see. That's called visible light. And sure, that is light. It also travels at the speed of light, but there are many, 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 many other types of light. And everything that you see on that electromagnetic spectrum is indeed a different type of light that has a different wavelength, a different frequency, but all the same is light and travels at the speed of light. So now that that's out of the way, let's answer these questions. So, which has a shorter wavelength, microwaves or UV? Well, to answer that, I will go to that electromagnetic spectrum that I posted on the classroom. So the important things, it looks kind of busy here. There's a lot of information. The most important things are the wavelength that you see at the top here. So this wavelength is measured in meters. It's often given the symbol, the Greek letter lambda, though it's not for some reason on this one. Often the wavelength is given that symbol. And the frequency down here, right? So that's the number of oscillations or number of times it vibrates in a certain period of time, often measured by hertz, which the short form HZ you see right there. And if you look, so we also have the radiation types, so the various types of light, approximate, things that are on of the scale of those various wavelengths, and then some sources. So what kinds of things produce those different types of light? And at the bottom, we have a measure of energy. So let me get that out of the way. And we'll talk about that as well. So the important things to note on this electromagnetic spectrum are that the wavelength is inversely proportional to the frequency, meaning the following. So as the wavelength gets larger, and in this, it's going larger from right to left. So this right here, 10 to the 3, is a much bigger number than 10 to the negative 12. 10 to the 3, right, means 1,000 meters. Whereas when you get to these negatives, right, so 10 to the negative 1 is actually 0.1 meters. So this is increasing in wavelength as we go from right to left. And since it's inversely proportional to the frequency is increasing as we go left to right. So if you have a very small wavelength, like 10 to the negative 12, like gamma rays, then you have a very high frequency. So that is the relationship that we have there. The second relationship that's important to note is that the frequency is directly proportional to the amount of energy that uh, those light rays or those photons of light possess. So if there is a very high frequency, then they also are high energy, and vice versa. Okay, back to the question. So the question asked me microwaves versus ultraviolet waves, which one has the shorter wavelength? Well, let's take a look. So we have microwaves right about here with a wavelength of anywhere from, maybe about 10 to the negative 1 to maybe 10 to the negative 4 or just a little bit less than that. So that's the range of microwaves. Ultraviolet is way over here. And if we look at UV, it's a much smaller number for the wavelength, 10 to the negative 7, right? So that to the power of negative means there's that many zeros before you get to the number. So we have UV in the range of 10 to the negative, almost -9, ranging up to 10 to the negative, just a little bit past 10 to the -7. So that's 0.000001 meters in terms of the wavelength, whereas the microwaves are just, about 0.1. So this is a much bigger number here compared to that over there. So UV has the much shorter wavelength. So let's type that in. UV has a much shorter wavelength. Okay, there's the answer to that one. Let's bold it. Now let's look at the next question. Now we're talking about frequency. So which has the greater frequency? Is it going to be gamma rays or radio waves? Well, let's go back again. So remember, frequency is increasing as we go left to right. Gamma rays are at the far end, super high frequency, also super high energy. And if we look at radio waves are to the left side of this picture. So it has a much lower frequency compared with gamma rays and also much lower energy. So let's say that. Hold you again. Gamma rays, a much higher frequency than radio waves. Okay, I know that you've been clamoring for more math. Mr. Sanford, I know it's June. I know it's a pandemic. I still want more math, is what I picture you guys saying. So let's do some math. And if the circumference of the Earth, give or take, is around 40,000 kilometers, of course, that depends on where we're measuring it, but let's just say it's 40,000 kilometers. How many times can a photon travel around the Earth in 1 second? So a photon, as you read, is like the smallest packet or parcel of light. And light is strange because it acts as both a particle and a wave, which makes it different than sound in that light can actually travel through the vacuum of space, whereas sound cannot. So light's special for a lot of reasons. Also, the fastest thing that we know of in the universe. So let's do some calculations here. So I'm going to write down some things that we know. So we know that the speed of light, which is the c in Einstein's famous E equals mc squared, the speed of light is equal to 300,000 kilometers per second. We know that. I put it in the note there. And that's roughly correct, give or take 300,000 kilometers per second. You can look up what it is precisely if you want to on your own. It differs slightly in a vacuum compared to what it would be like here on Earth where we have an atmosphere, and even more so, as you'll see later on in this unit, when it goes through certain objects like water or glass or something like that. So that's the speed of light. We know that. We know that the circumference of Earth is equal to 40,000 kilometers. So we know that in 1 second, a photon of light is going to travel around the world many times, right? Because it goes 300,000 kilometers in 1 second, and the circumference of the Earth is only 40,000 kilometers. So it's going to go many times around the Earth. How many? Well, we need to do a little bit of math. I'm going to bring up my calculator here. So we're going to take 300,000, and we're going to divide that by the circumference of the Earth, which is 40,000, and that gives us 7.5. So 300,000 divided by 40,000 equals 7.5. We can finish it with a little sentence. Photon of light will travel 7.5 times around the Earth in 1 second. Good. All right. We're on a roll now. So let's do some more math and figure out the distance that light could travel in 1 year, which is indeed called a light year. And if you remember from last year, when you took astronomy, a light year is a distance a distance to measure similar to a kilometer or a meter or something like that. It just measures really, 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 really big things, like distance between objects in space. So that's exactly what a light year is. The distance that light can travel will travel in 1 year. So how do we figure that out? Well, I told you what light was in kilometers per second up here. So I'm going to write down the things that we know. So we know light goes 300,000 kilometers in 1 second. I don't want 1 second, I want 1 year. So let's take that number and let's multiply that by, well, let's first figure out how far that will travel in 1 minute. So we'll multiply that by 60 to figure out how far that light will travel in 1 minute. Now, if I want to figure out how far that light will travel, not in 1 minute, but 1 hour, there's 60 minutes in an hour. So let's multiply by 60 again. Getting closer. How about 1 day? Well, there are 24 hours in a day. And then if I'm now at the point where I want to figure out a year, there are 365. Oops. There are 365 days in a year. So I'll go to my trusty calculator and do that math. Let's clear you. So we've got 300,000 times 60 times 60 times 24 times 365. And that equals a very large number. That would be 9,460,800,000,000 kilometers in 1 year. So if you want to know what a light year is, it's 9,460,800,000,000 kilometers. A far, far, far away. Let's see if I can just copy that number so I don't have to type that all out again. So that altogether equals that number. In 1 year. Good. Okay. What type of technology uses electromagnetic waves that have a wavelength approximately equal to your height or how tall you are? Well, again, let's go to our electromagnetic spectrum and take a look. So let's say that, most of us are in between are 2 meters or less in terms of our height. So we're looking in the range right here. So here's 10 to the 1, here are human beings, and we're looking at what type? Looks like radio waves. So radio waves have a wavelength approximately uh, equal more or less to the height of average human beings. And the wavelength is just like it sounds, it's the distance between two waves. So you can imagine waves in the ocean, and you could count the distance between two peaks or the distance between two troughs in those waves. Same thing with the wavelength of light, that's the distance between two waves. So we're looking at radio waves as the answer to this question. Last one. Electromagnetic waves with very high frequencies are dangerous to living organisms. So I've asked you why you think that might be, and then to give an example of this type. So if we look at our electromagnetic spectrum again, very high frequency is to the right. So that's things like UV, pardon me, X rays, or even things like gamma rays. And you kind of know just based off experience that these can be harmful. For example, ultraviolet rays, that's what we protect ourselves from when we wear sunscreen. So UV can damage, can cause mutation, like we learned about in biology, and that can lead to things like cancer, skin cancer. X rays. So you know that when you go to the dentist, and they do an x-ray of your teeth or gums, the dental hygienist or the dentist, they get out of the room, they go behind a lead barrier, they put a lead vest on you because the x-rays won't penetrate that, because the x-rays are great to see through soft tissue and see hard tissue. However, you don't want to get continual exposure to x-rays because, again, they will damage your cells, they will damage the DNA, and that could lead to harmful mutation. Same thing, of course, with all the way to the far extreme gamma rays, which luckily we're mostly protected from due to our magnetic field that we have around the Earth, around the planet. But all of those share in common one thing, and that's those super high frequency, so really, really high frequency, but really, really small wavelengths. And in fact, those wavelengths are so small that they are shorter than the diameter of an individual cell. And therefore, they can actually damage the cellular structure. And in particular, they can cause damage to the DNA. And as we know, if you mess up those ACTs and Gs, those sequences, it can lead to mutations, which for the most part are benign, meaning they don't, because remember, any given mutation anywhere doesn't necessarily cause a problem because only 2% of that individual strand of DNA is actual coding regions or genes. The rest is are non-coding regions. But we know that if a mutation does have an effect, it's likely to be negative. And any of those wavelengths that are super small, high frequency, those wavelengths that are shorter than the diameter of an individual cell are able to cause damage. Right. So let's write that in. So that's weird. So very short wave radiation that is high frequency cause damage to DNA cells. Is this can lead to harmful and examples include UV, X-rays, and gamma. Okay, that's it for these questions. Again, if there's anything that you didn't understand or you wanted further explanation on, just type it in the comments. I will also, of course, post this answer key. So if you wanted to skip right to that, well, I guess you would have already done that because I'm at the end of my video. All right. I hope you guys are doing well, and hopefully you get a chance to go outside, enjoy the sun with some sunscreen so we avoid that damage we just answered in question 6. All right, guys. Um, Next, we'll talk about maybe not tomorrow, but I will post either tomorrow or the next day about how light is produced. And that's it for me.